Okay, so it looks like most people are here. So I'm going to get started in a second. There was one thing, so on Canvas, you may have seen that there was a page called Info About Workshops. That wasn't supposed to be on this Canvas page. We don't have a workshop set up. It's definitely not mandatory. I was thinking of having my TAs run a problem session, but if they do, it will be optional. So you could come and show up to that, but you don't have to. It would be remote, just like this class. So I'll keep you posted on that. It would not start until next week at the very earliest. So, but do let me know if you think that you would go to that and you would be, interested, so I can know, yeah, whether or not to do that. Okay, so hopefully you guys can all see my screen right now. Do you guys see that? Right here?
Yeah.
Okay, cool. Okay, so everything's working. So we're going to start off talking about linear systems of equations. I don't know how far we're going to get today. I kind of made the course schedule a little ambitious, and I'm not sure that we're going to stay on track even in the first week. So unfortunately, but we'll do our best. So basically, we have to start off with a bunch of definitions. So that's what today is going to mostly be, right? So this is going to be a bunch of definitions. Okay, so first off, we have a linear equation. And this is going to be an equation of the form we would have a1 x1 a2 x2 to an xn equals b. Okay, and so when you're looking at this equation, what you should see here is the x1 up to xn, so each of these guys are supposed to be variables. So these are the variables. And then a1 up to an and b, so all of the ai's and then b as well, these are constants. Okay, so just keep those separated. So we use xi for variables. We'll just always use those to be variables. And then a something, a with a subscript, or b, or any other letter like that, we usually use for constants, okay? So constants meaning real or complex numbers. Right? But for us, mostly real numbers. We probably won't get into complex numbers much at all if we do. Okay, so something, okay, so first of all, the constants, a1 up to an, those numbers have a special name. These are called coefficients. So these are the coefficients of the linear system, or sorry, not linear system, of the linear equation. I guess the coefficients. Right? Okay. So this is similar to how we refer to numbers in front of polynomial, or the numbers in polynomials, we refer to those as coefficients, right? So similar definition, but unlike polynomials, you shouldn't see any powers on your variables. So that's going to be the difference between a linear equation and a polynomial equation, right? So just to make this really clear, we'll look at some examples. So for instance, if you had something that looked like this, 3x2, let's say cubed, plus 4x 3 equals 1, right? This is an equation involving some constants and some variables, right? But since we have these, I'll do this in another color. Since we have x1 being raised to a power and also x2 being raised to a power, that means that this is not a linear equation. Right, so we need that x1 to be raised to the power 1 or just not raised to a power. You can see it either way. You shouldn't see exponents in your linear equations. So that's what makes them linear. Okay. So other things that would not be allowed in a linear equation would be things like if you had a product of two variables like x1 times x2, like this, something like this. This is not a linear equation because you have your two variables being multiplied together, right? So they need to be each in a separate term, right? You also can't have like square roots. That's also by like being raised to some power. So these are all non-examples of linear equations. So here, the issue would be here and also here. Great. Okay. But the following is a linear equation. So something that looks like natural log of 2 times x1 plus square root of 7 times x2 sine of, I don't know, 3. Right? So even though these constants look a little strange, right? They are still just numbers. They're real numbers. So these are fine to be constants since our variables are just plain by themselves. We just have x1 times a constant. We have x2 times a constant, x3 times a constant. That's fine for a linear equation, right? Okay. So you just have to look at the variables, like make sure nothing strange is going on with the variables. You have a linear equation. Okay. Okay. So let's see, I'm going to skip over that. One thing I did want to mention though is that in this class and in a lot of math classes, n, when we use the number n, it's always a natural number, meaning a positive integer. Okay. And then before I get too far, I do want to go over something real quick, like notation wise. So you may have seen this before, this like R written with like 2 lines. This is the notation that we use for the real number line. So just, you know, your regular number line with 0 and all the other real numbers, right? So this will be our notation for this. And then we also have the Euclidean plane. So in this class, you can think of this as like 2 copies of R, right? You have one being your first axis and another on your second axis. And so the notation that we use for this is R2. Okay, so like for 2 copies of R. Okay, this is the Euclidean plane. And then we can keep going with this. So here if we take 3 copies of R, we get 3-dimensional space. And this will use R3. So this is like 3D space. And then if we keep on going, we can just keep on adding copies of R. So we'll use Rn for a general, or it's not general, but n-dimensional space, which will come up later. Okay. But so this is just the notation that we use. Okay. Now, so like I said, we're going to talk about systems of equations. So you're probably familiar with solving systems of equation. Oops. So a system of linear equations is just what it sounds like, just a collection of linear equations. Right? So EQS is the abbreviation I use for equations. So I'll probably use that a lot. Okay. And so for example, something like minus 3, something like this is a system of equations. I just have those two grouped together. I get a system. So you probably know how to solve something like this. You probably have plenty of practice doing this, right? But if you're given something that's a little more complicated, so like consider another system of equations, say like this, 5x1 minus 2x2 equals 8. And I'm sort of like stacking these so that the variables line up, right? So here's another system of equations. It's a little bit harder to solve, right? Maybe it's not immediately obvious how you should go about doing this. You could probably fuss around with it and figure out an answer, right? But the idea that we're going to introduce here is how to solve these systems of equations for even larger systems with more variables and more equations, and come up with basically a nice way of solving any system of equations, right? So no matter how complicated it is, you could have 5 variables and 5 equations or something like that, we'll be able to deal with it, okay? So we'll come back to this particular example. Actually, we're gonna continue. So it turns out, so I'm just gonna tell you that 1.5, and 0.5 is a solution of this system. So when we write down solutions in this class, we're going to write them as ordered lists like this. So this is going to be for each entry, that will be the value of x1, x2, x3 in order, right? Okay. So just to write out what the actual definition of a solution is, it means that this is an ordered list. So S1, S2, up to Sn, however long that might be, is a solution of a linear system if plugging in basically S1 for x1, S2 for x2, etc., all the way down, if doing that satisfies the equation. Right? Okay, so we can check that this, so this thing that I told you was a solution of this system is actually a solution, right? Just by plugging it in. So what we would do is start with the first equation and we just plug in 1 for x1, 1.5 for x2, and 0.5 for x3. And if we add those up, we just get 0. So it does satisfy the first equation because we got that the left-hand side, when we plugged it in, is equal to the right-hand side, which was just 0, right? Now, to check the second one, again, we plug in 1 for x1, 1.5 for x2, and we want this to simplify to 8, right? So that's what's on the other side of that equation. So we would get 5, wait, oh, this should be a plus, sorry about that. Here we go. 5, and then 2 times 1.5 is 3, so this does actually equal 8. And then we can check the last one, so 2 times 1.5 plus 4 times 0.5. This will simplify to 3 plus 2, which is 5. Right? Okay, so this is a solution. Okay. Right, so that's all it means for something to be a solution. Okay, this is the definition. Now, so thinking about what happens when we have 2 equations and 2 variables. So this one is something that we should be familiar with, so we'll start there. 2 equations and 2 variables. So for example, 6 and x, something like this, right? We know that these actually represent lines in R2, right? So we could plot them out, figure out what they would be. So let's go ahead and do that. So the first one, probably the easiest way to graph this is just to plug in 0 for x1 and see what x2 would have to be, right? So if we plug in 0 for x1, x2 should be 2. So that would correspond. So here's my x1 axis, x2 up here. X1 is 0, then x2 is 2. So that would be a point on my line. And then if x2 is 0, x1 has to be 3. So it would look like this, right? And then I have 2 points on the line. I can graph it like that. Okay. And then for the second one, we can do something similar. So if x1 is 0, x2 is 2. So it actually goes through that same point there. And then if x2 is 0, x1 is minus 2. So we get this line right here, right? Okay, so when it comes to systems like this, these are represented by lines in R2, right? And a solution of the system corresponds to an intersection point of those 2 lines, right? Okay. And now there are some things that we know about intersections of 2 lines, right? So it's a fact that we know from geometry or, previous math classes. So given 2 lines in R2, so we can have one of 3 things might happen, right? So first of all, they could intersect at exactly 1 point. So just like the example we just looked at, right? What do you think another possibility would be?
They could be the same line, infinitely many solutions.
Yeah, they could be the same line.
They could also be parallel and never intersect.
Yeah. Okay. I'm gonna write the parallel one first because it's a little yeah. They could be parallel. Let's say they are parallel. So that means no intersections. And they could be the same line. So there's nothing saying that given two lines that they couldn't be the same thing, right? So they could be the same. Which would mean that they intersect at all points.
Infinitely, basically.
Yeah, exactly. At well, not all points on
In the domain.
the line. So infinitely many points. Yeah, exactly. Okay, so this is just the case when we're talking about two variables, right? But this is actually true for any linear system of any size, right? So what we can say is that any system of linear equations has either exactly one solution, right, corresponding to that one intersection point. So if it has exactly one solution, it has a unique solution, right? Or it has no solutions, which happens when the lines do not intersect, right? Or finally, it has infinitely many solutions. Right? So it's kind of interesting to think that this is what happens when you have a system of linear equations, right? So you either have exactly one or you have infinitely many, and there's no in between, right? So that's what we're dealing with.
So this applies to like no matter how many variables you have,
Mhm.
you get either one of these possibilities.
Right. So what you can think about is, let's say we go up one dimension. So say we have three variables, right? So we're
Right.
looking in R3. I'm going to try to draw something and we'll see how it goes. Okay, so your system, let's say you had a system of equations. I'm not gonna make up goodness. Okay, so let's say you had three equations, three variables. What could happen is, in fact, I'll get rid of these. When you look at one of these equations, this represents a plane in R3, right?
Right.
Okay, so you could have like a plane, and then you have another plane represented by the next equation, and that could look something like this, right? And they'll intersect in a line.
Right.
And then if you have another plane, say, that goes through the same line, then you would get infinitely many solutions along that line.
Uh-huh.
But if it didn't intersect along that line, it would sort of force it to be a unique intersection point. It would just be,
Okay.
yeah, okay. So that's how these things work. Sorry about the drawings, they're great. But I think there's some pictures in the book somewhere. So I'll pull them up if I can find them. Okay, so some more definitions now. So a linear system is said to be consistent if it has at least one solution. So if we're in the case that you get exactly one solution or infinitely many solutions, in both of those cases, the system is consistent. Okay. Otherwise, if it has no solutions, then we say it's inconsistent. Okay. So, right. So one thing to note, if a system has, so we're going to go through those three possibilities. So if it has no solutions, like I said, that means that it's inconsistent. If it has one solution, then it is consistent, and also that solution is unique, right? So, okay, so we have those, and then if it has infinitely many solutions, that means that it is consistent, but that the solution is not unique. Okay, so this is getting into something that mathematicians really care about, which is existence and uniqueness, right? So it's, does there exist a solution for this problem, and is it unique if we find it? And so we'll be able to tell from some operations and looking at systems whether or not we get existence or uniqueness. Okay. Okay, and then I think two more definitions. So how are we doing on time? Okay, fine. So the set of all possible solutions of a system is called the solution set. And then two linear systems are called equivalent if they have the same solution set. Okay. All right. Okay, so now we're going to start talking about matrices. And in this first part, we're going to be using them to represent linear systems. Okay, so matrices, this is plural of a matrix, which is one. And similar to like an ordered pair, which you've dealt with in mathematics, it's just an arrangement of numbers. It's just a way of arranging numbers. So it's just going to be really convenient for us to use in the context of linear systems to organize that information. Okay, so a matrix looks like, so we use square brackets around all of the numbers. So you just have some numbers that look like this. Right, and then you close it off on the other end with another square bracket. These we refer to as the rows. So each one of, so there are three here, right? And you could just pick one off and you call that a row. So this 1070 is one row, and then another. You had a question?
Yeah, so in the second to last definition you gave that says a set of possible solutions of a system is called a solution set. Is there, I don't know, because I'm thinking like, whenever I think of like multiple solutions for a single set, I'm thinking of like non-linear equations. Will we have like multiple solutions to a solution set? Okay.
Yes, so but the thing is that since we already said that we either get one solution or infinitely many, our solution sets are going to have like a particular form. So unlike a polynomial where you might have like, okay, so the solutions to a polynomial equation is just like 1, 2, 3, 4 or something like that. For us, it's either going to be just one solution, so it'll be like a set containing one solution, or it will be infinitely many, and we'll have to figure out how to write that down. So we'll have a
Okay, got it.
way of writing those down.
So then in the case of like no solutions, we just write an empty set.
Yeah, exactly.
Okay.
if there are no solutions. Yeah. Right, yeah, I would like to see your faces just because I can like gauge your reaction. So that's nice for me. Yeah, hi everybody. Okay, great. Let's see. So here are, oh, whoops. So far we have rows, and then just cutting it vertically, we have the columns of the matrix like that. And then any of the particular numbers in here, like these ones right here, these we call the entries. Okay, great. So this particular matrix has 3 rows and 4 columns. So we say it's a 3 by 4 matrix. So we use this X, and you read this 3 by 4 matrix. And this is what we call the size of the matrix. So it's not really like one particular number. We have to know the number of rows and the number of columns, right? So notice the rows always comes before the columns. So it goes rows by columns. There's a good reason for that. It's just to keep consistency. It comes up later, but just so you know, this is how we do it. So rows first, then columns. We usually use M for the number of rows and N for the number of columns. So you will probably hear reference to an M by N matrix. This isn't basically a matrix of arbitrary size. So we're not really like setting what size it is. We're just saying it has M rows and N columns. Okay. Okay, and like I said, these are going to help us represent linear systems. So the connection to linear systems is the following. So going back to that system that we had before, this 3 by 3 system. Well, I guess maybe I shouldn't call it that. The system here, 5x1, 2x2 equals 8, and there we go, this one. There are 2 associated matrices with this linear system. So the first one is the matrix of coefficients. So we just take all of the coefficients and we stick them into a matrix. So starting with that first variable in the first equation right here, we would put a 1 there. And then the coefficient for the second variable in the first equation is -1. And then we get 1. Next, we have the second row, we get a 5, 2, and then since there's nothing there for x3, we put a 0, right? In the third row, we also put a 0 for the first variable, and then we have 2 and 4. So we just stick all of those coefficients into a matrix, right? Oh, I guess the matrix of coefficients. And then the second associated matrix is called the augmented matrix. And what this is basically our matrix of coefficients. And then we also have these other constants that are on the right-hand side of these equations, right? So we're just going to add those on as another column. So just to keep those separate in our minds, we'll draw a vertical line and then draw or write in those constants there. So this is our augmented matrix. Okay. I will say that in the book, I don't think they do draw the vertical line, but I will in class, just because I think it helps visualize what's going on, right? So, yeah, just so you're aware of that. So we can use this to solve systems in a more efficient way. So if you go and look at the textbook in section 1.1, I think the first example, they do go through solving a system using, standard techniques and do that alongside using the matrix techniques that we'll learn, right? So if you want to see that, just to see what the connection is, I would recommend you go read through that. But I'm not going to go through that because it's really long and tedious. And so it'll just take up a bunch of time. But I do think you should at least take a look at it because it can be enlightening. But what we can do is we can do some operations on this matrix that will not change the solution set. Okay, so we have some operations that will not change the solution set. So one obvious one should be that we can interchange the rows, right? So I don't know if this is how I wanted to explain this, but anyways, interchanging the rows is just the same as interchanging two equations. So writing one above another, it really doesn't change the solution set, right? So we can move them around, we can change the rows around. It doesn't change the solution set. Another thing that we can do, which you may know as a technique for solving systems of equations, is we can add two equations together, right? And that doesn't change the solution set. We can even take one of those equations, multiply it by a constant, and then add it to another one, right? Okay, so in the context of matrices, you don't want to delete a row from your matrix, right? You want to always have the same number of rows. So what we'll do is, what we can do is replace a row by, how did I word this? By the sum of itself with a constant multiple of another row, right? Okay, and then the last one is also kind of obvious that you can scale, so meaning multiply each entry in a row by a non-zero constant. Okay. You can't multiply by 0 because that would just delete everything, all of the information that you have. But
and that scale, that's going diagonal from left to bottom right, yeah?
no, so it would be like, for instance, here, you could multiply by a constant, say like 2 across the top row, and you would get 2 minus 2 to 0. So you want to go straight across the row.
Okay, I was thinking like scaling matrices with dot multiplication.
Nothing that complicated.
Okay.
So these are what we call elementary row operations. So yeah, we're not doing anything with dot products yet at all.
Okay.
Did that answer your question?
Yeah, I had one more, but I forgot it.
Okay, just interrupt when you remember. Okay. Right, so like I said, these are called elementary row operations. Okay, and so they don't change the solution set, but they do simplify our matrix down to something where we can figure out what the solution will be pretty easily. Okay, so right, okay, so another definition. So if you can move from one matrix to another using elementary row operations, we say that those are equivalent, row equivalent. We say that the matrices are row equivalent. Right. So any matrices that are row equivalent will have the same solution set, meaning they are just regular equivalent as well. Okay. Okay, so we're going to go through an example of using these row operations. So starting with, let's see, we'll have 1, 1, 1, 3, 2, minus 1, 0, 1, 0, 1, 1, 2. Okay, so this is our matrix we're starting with. I'm actually going to move this down a bit since I need some more room. Right. And how I want you to do this when you're writing out your work is to write the row operation that you're going to do above an arrow. And then you'll use the arrow to denote you're moving to the next piece of your simplification, and then, you know, do that. Otherwise, it's really hard to like follow your work if you don't like tell me what you're doing. Okay, so in this case, let's see. I'm gonna move this over just a little bit more because I wrote really big. First off, we're gonna label the rows. So I'll use R1 for the first row, R2 and R3. That's how we're going to refer to them. Even if we flip them, so say we interchange row 2 and row 3, we're not gonna relabel them. Wherever they are in the matrix, that's the name of the row, okay? So I'll show it. You'll see what I mean, I think, in a second. So the first thing I'm going to do is take row 2 and replace it with row 2 minus 2 times row 1. Okay. And so just to like completely show my work, I'm going to write this up here. So my row 2 is 2 minus 1, 0, 1. And I want to multiply row 1 by -2. So I'm going to write row 1 times -2 underneath it. So -2, -2, -2, -6, and then add them together, like entry at a time, right? So in the first entry of the row, we'll get 0, then -3, -2, and -5, right? Okay, so everything else stays the same, and then we just replace row 2 with that thing we just computed. So row 2 will be 0, -2, -3, -2, -5, and then the others just stay the same. Right, okay. So it's definitely recommended that you only do one row operation at a time. Otherwise, it gets really complicated. So yeah, make sure you do one at a time. Okay, next, what I want to do is swap row 2 and row 3. So I'm going to denote that like this with the two-sided arrow. That means I'm just switching positions. So I'll put row 3 in the spot for row 2 and the other one in the next spot. So it will look like this, right? And then the last operation I'm going to do is I'm going to replace row 3 with row 3 plus 3 times row 2. Move this over just a little bit. Okay, so let's do our work off to the side. So row 3 is this last one here. Like I said, we don't change the labels. So it's 0, minus 3, minus 2, minus 5. And then we add row 2 times 3. So row 2 times 3 would be 0, 3, 3, 6. And then we're just going to add these together. Okay. So we would get 0, 0, 1, 1. Right. So our answer or our reduced matrix will be 1, 1, 1, 3, 0, 1, 1, 2, 0, 0, 1, 1. Okay, like that. Okay, so now we have it in this form. So I know I just like kind of did a bunch of stuff and it's not really clear like why is this better than what we had before. But what I was looking for was this kind of what we have now in this form, we have ones along the diagonal, right? So the diagonal meaning just starting at the top and just moving down in a diagonal manner. And that's going to make it easy for us to solve. Okay, so this is what we'll eventually call a triangular matrix. So it has this sort of triangular shape, right? So if we were to like imagine a triangle like this, right? And when we have this triangular shape, we can do something called back substitution. So once a matrix is triangular, we can use back substitution to find the solution. Right? Okay, so the reason being that if we look at this matrix and we know that this represents a system of equations, so we're kind of going back from, we wrote our system as a matrix, now we're going to write our matrix as a system, right? So this would give us x1 plus x2 plus x3 equals 3, and then x2 plus x3 equals 2, and then finally x3 equals 1. So we already know what x3 is going to be. Then we can just substitute that into the previous equation to figure out what x2 is going to be. So x2, replacing x3 with 1 equals 2, we get x2 equals 1. And then we use both of those to substitute into the top equation and figure out what x1 is. So we're kind of like piggybacking backwards, right? So we get x1 plus 1 plus 1 equals 3. So x1 equals 1 as well, right? So our solution is 1, 1, 1. It's unique. We just have one, and that is it. Okay. Let's see. Now, there is a particular name for this form that I found, this sort of triangular form. Since we had, but it's actually going to be more general than this, and it's what's called a row echelon form. So this form This is called the row echelon form, right? And it's nice because we can pretty easily determine the solution set or figure out if a system is inconsistent from this, okay? So once in this form, it's not hard to determine the solution set or tell if the system is inconsistent.
Will most solution sets that we come across, will you be able to put it into this form, or is this something that like only some solution sets are able to do with?
No, we will be able to put it in this form. So we'll have an algorithm that you'll follow. It'll always work. And so basically for any linear system, you can figure out whether it has solutions or not. Okay. Let's see. Okay. Cool. So okay, so I'm gonna go over like the definition of this row echelon form, but it sounds a little weird and it's a lot easier to understand if you look at examples. So I'm just gonna write out the definition and then we're gonna look at examples. Okay, so first we have two definitions that we'll have to go over. So a row is non-zero. I mean, this one kind of makes sense if any of its entries are non-zero. So if you have all zeros, that's a zero row. If anything in there is non-zero, it's non-zero, right? Okay, and then an entry is called a leading entry. Leading entry if it is the first non-zero entry of a row moving left to right. So for example, here is your leading entry in this row, and then it's not until the third entry in the second example, right? So just the first non-zero.
So the leading entry of row 3 on our previous example would be the third column?
Up here? Yeah.
Yeah.
So it would be that one right there. That's the leading entry. Okay, so that's all we need to define. So now we can talk about row echelon form. So apparently this echelon, the reason it's called this is because of it sort of looks like steps. So you'll see that, well, we can even look at this. See, it kind of moves down in steps like that. So that's the sort of shape that we're going for here. Okay, so there are three conditions. We need to have that all non-zero rows are above any rows of all zeros. Okay, so if you have any zero rows, they're all the way at the bottom. Okay. And then each leading entry is going to be, so each leading entry of a row is in a column to the right of the leading entry of the row above it. So we'll see that in a second. And then all entries in a column below a leading entry are zeros. So I'll just fix this up a little bit. Okay, so these are your three conditions. So I'll give an example here. So one, two, okay, so this is in row echelon form. Okay, so let's look at why. So we don't have any zero rows of all zeros, so the first condition is satisfied automatically. Each leading entry of a row is in a column to the right of the leading entry of the row above it. So we don't have to check this for the first row because there's no row above it, right? But for the second row, the leading entry is right here. It's that 2. And then you want to have that it is in a column to the right of the leading entry of the row above it. And so the leading entry of the row above it is right there in the first spot. And this column is definitely to the right of the first column. So that's what that means, right? And then we can check for the next row. The leading entry is right here. And this column is to the right of the previous column of the leading entry. Does that make sense? So it's like you have this step down and over, right? You have nothing below, sitting below the leading entry of the previous row. Okay. And then all entries in a column below a leading entry are zeros. So you can see that there are zeros below that leading entry, zeros or just 1 0 below this leading entry, and then the last one. It doesn't need to satisfy that, right? Okay, so this is in row echelon form. Now let's look at an example that is not in row echelon form. So we could have, let's say 1 1 3 5 6 3 0 1. Okay, so this is not in row echelon form. Can anybody tell me why?
Because the 1 is where 0 should be.
Yeah, exactly. So it's not satisfying the third condition where it says that there should be a 0 below a leading entry, right? So just to write this out. So this is not 0, and this is the leading entry. Okay, and then just one more example here, just because there's something else I wanted to point out about it as well. So
You
if you
could turn that into a, you could put that in row echelon form if you were to do an operation with the second row, right?
yes, yeah, you could replace the, so you'd want to replace the third row with, well, you just have to figure out a way to get rid of that 1, basically. So yeah, you could replace the third row with, so row 3 goes to, oops, I put that in.
Like
It's
row 3 minus
yeah, 1.
0.5 row 2.
Yeah, exactly.
Yeah.
Yeah. So yeah, you can manipulate it to be in row echelon. Okay. So here we have this one. This is in row echelon form, right? So you can check that it satisfies all of those conditions. There's something else about this that is interesting or different about this. This is an inconsistent system. The reason being that in the last row, you get, if you were to write out what this means in terms of the linear system, you have 0 times x1 plus 0 times x2 plus 0 times x3 equals 3. So you get 0 equals 3, which is not true, right? So this is sort of what you will see when you have an inconsistent system, is you'll get something like this in row echelon form. So that's why the row echelon form helps us see when a system is inconsistent and also see the solutions when it is actually consistent. So yeah, you'll get something like this where you have all zeros and then a non-zero number in the augmented part, the column. Okay. So because this is not true.
Scroll back to the conditions for the row echelon form.
Yeah, right here.
Okay.
Will we be reviewing any of this on our next class? Because this is a lot.
Yeah, yeah, we'll be doing, I needed to get an idea of like how fast I should be going. I kind of wasn't sure. So turns out we should be going a lot slower, I think, than like originally intended. So I'm just going to go over one more thing, reduced row echelon form, and then I'll give you some things to work on at like until the end of class. So we won't cover any more past that. You can work on some problems and then I can review this as well at the beginning of the next class.
Thank you. I feel like I'm struggling a bit right now.
It is a
Um,
yeah, so no, it's okay. It's a lot of information like all at once, I know, and you just have to like dive in and try to get used to these things. Okay, but we'll be working with them a lot this semester, so hopefully you'll get enough practice. Okay, so here is row echelon form, and then there's one more thing, like I said, so it's just a little bit better than row echelon form. It's called reduced row echelon form. Okay, and so the conditions for this, it should be in echelon form. So in regular row echelon form. And then also each, oops, one more definition before we can do this. So actually, I won't define that yet. We'll do that next time. So each leading term, leading entry is going to be 1. Okay. You can achieve this by just like multiplying by a scalar if it's not 1, right? Or a constant if it's not 1. And then each leading term is the only non-zero entry in its column. So instead of just having zeros below it, it also has zeros above it. So there's nothing else in the column that is not 0 when you have a leading entry. Okay, so here is an example of a reduced row echelon matrix. So we should have 1s always as a leading entry. So 0, 1. Okay, so let's look at focus on the leading entries. So that would be this one here, In the next row, it's that guy. In the third row, it's this one. And then there's no non-zero entries in the last row. So we can see already that all of those leading entries are 1. We can also see that we have this like step-like behavior. So it is actually in regular echelon form. So this is in row echelon form. We have leading ones. And then the leading term should be the only non-zero entry in its column. So for the first one, you can see that these are all zeros. In the second column, or corresponding to the second leading entry, we only have zeros other than the 1. And then here in this, that would be the fourth column. But yeah, there's only zeros in that column as well.
Is it okay that it skips the third column, that it's just like one larger step and then?
Yeah, exactly. Yeah, that's okay. So
If-
that's what,
Sorry.
yeah, go ahead.
2 questions.
Mhm.
The first is, I know you mentioned above that that row of zeros can mean that it's non-constant. I might have missed that. Sorry, I'm writing notes at the same time, so I sometimes don't hear everything.
Yeah.
So will a row of zeros mean that it's non-constant?
You mean inconsistent?
Yes. Sorry, inconsistent.
Yeah, not in this case because we don't have a non-zero number in the last column. So see, if we wrote out what this means for the,
Okay.
it's
yeah.
just like we would
Yeah.
get 0 equals 0.
That makes sense. Okay, so a row of zeros means an inconsistent solution when the augmented column is not 0.
Right. Yeah. When the augmented column, has a non-zero.
Yeah.
Yeah. Exactly.
And I know I asked this question about the normal echelon form, but it's now that like we've been over how to like make normal echelon forms, I can see how like every single set of solutions can be put into normal echelon form.
Mhm.
But because everything is linear and we're scaling it and we're scaling it like linearly, there's like no rotations or anything. I don't really see how like every single set of linear equations can be put into reduced row echelon form. Whenever there's a 1, there needs to be there needs to be zeros above it.
Yeah, so that is going to be part of the algorithm that we'll have for putting it in reduced row echelon form. So maybe you can see that you could take a system and put it in row echelon form. There's a way of then moving backwards to get rid of those values that are above the leading entry.
Okay.
Okay, so we'll get to that.
I have a question. So I'm trying to figure out, in the textbook, it calls them the pivot points.
Yeah.
And at one point it said like this needs to be in the leftmost column. But then other times there's like a space in between the pivot points, like you see here, the column with 2 2s and 2 0s.
Mm-hmm.
I guess just like, how do you know when it needs to be all the way to the left?
Okay, I'm just cleaning this up. So I'm not sure do you have like a position in the textbook you're referring to?
Yeah, sorry, let me find the page. Sorry, I should have prepared this before I asked the question.
Yeah.
Where did it go? I am very sorry.
Okay. So I will say that so a
I found it.
Oh, okay, yeah. Go ahead.
Sorry. It's on page 14. It says the pivot position in the second row must be as far left as possible, namely in the second column.
Is it in the example or?
Yeah, it's an example too, all the way at the bottom of page 14.
Okay, it probably has something to do with the example.
Okay, thank you.
Yeah. It doesn't necessarily have to always be like, you see that we did skip a column here. And that's because the next leading entry isn't in that column, it's in the next one, right?
Can I ask a question?
Yeah, go ahead.
So as much as I understood in the fourth column, fourth row in here, these are like the coefficients, right? So why do we write the 0? Like, why do we write the 0, like the all 0 row? It doesn't, like, if it's gonna be the, like, at the end, if it's gonna be 0 equals 0, why do we write it?
So you usually won't like start out with that, but sometimes when you're doing your like your row operations, right? You'll end up with a row of all zeros. So you don't usually start out with a matrix that looks like this with all zeros, but you could do some operations and then end up here. And what that means is really that one of your rows was a multiple of another. That's like why it would disappear.
So like, would I just like stop using that row or just like keep writing all zeros?
Yeah, you should keep writing all the zeros. Yeah.
Okay, thank you.
Okay. Let's see. We've got 10 minutes and I don't know if I wanted to.
Will these notes be up on Canvas?
Yes, I will figure out how to post the notes and then I mean I can post the notes, I just have to figure out how to do it so it doesn't look like one giant long page. So I'll figure that out. And then I'll also post, like, I'm recording this lecture, so I'll post the lecture as well. So you can like go back through if you needed, you know, to see it again or something like that.
Thank you. I appreciate that.
Yeah, no problem. Okay, so before I forget, I was going to say that a pivot, since it was mentioned, a pivot is really similar to a leading entry. It's really just a leading entry in a row echelon matrix. So when by row echelon matrix, I mean a matrix in row echelon form, right? Okay, so when we're referring to these, when we're talking about a matrix that's in row echelon form or reduced row echelon form, we'll call them pivots. Otherwise, they're leading entries. And that's because when we have it in this form, they have like a more exact meaning, right? They have like a more concrete and important meaning. And so we have a different name for them. Did you raise your hand again or was it raised from before? Hunter?
Oh, sorry, it was raised from before.
Okay, yeah, no problem. Okay, so I can either go through an example or I could give you a problem to work on. Which would you prefer?
An example, maybe?
Problem.
Yeah, I think an example.
Okay, I think you got outvoted. Does anybody else have an opinion?
Why don't we do a small example first and then a small problem that
Yeah.
follows that example?
Okay. I'll try to do that. We'll see if we have enough time. Okay, so example. So here we have, I'm going to write out the system and then the augmented matrix that's associated with it. So just looks like this. So we have 5 variables and then 3 plus x4 plus 5 equals 7. And then 2x2 that's it, equals 6. So 5 variables, we have 3 equations. We write down the augmented matrix. We would have 1s all the way across the first row. And then we'll have 1, 1, 1, 7, and then 0, 2, 0, 0, 0, 6. Okay, so this is our augmented matrix corresponding to this system. And then we're going to do some row operations to reduce it. And before we even start like, well, before I give you like a roadmap or like an algorithm for you to do this, it is kind of intuitive. You just kind of know how you want your matrix to end up and you just start doing things. And you might do something, you can always undo it. It's not really like there's a set, you know, you need to go in this particular order, right? So I think it's almost better to have just an idea of where you want to end up and just try to move towards it instead of, I'll give you an algorithm, but it's kind of long and sounds kind of complicated and makes it sound more complicated maybe than it really is, right? So, okay, what we're gonna do is we want to get this in echelon form and ideally in reduced echelon form. So notice that we have this first row and it almost lines up with the second row. The second row has got all these like ones that are the same as the first row, right? So if we were to replace the first row, so row 1 with row 1 minus row 2, it would get rid of all those ones, right? In the second through the fifth column. So we can do that and sort of simplify what's going on a great deal. So replacing row 1 with row 1 minus row 2, I guess I'll write this out since we're just starting out. So that's the first row. And then we want to subtract the second row, which is just 0. So I'll just write this as row 2 times -1. So it'd be 0, -1, -1, -1, -7. And add these together. Oh, oops. We would get 1, a whole bunch of zeros, and then -6, right? So we can just put that in for our first row. 1, 0, 0, 0, 0, -6. And then the second row we leave alone. So we don't want to do more than one operation at a time. Okay. And then what we can do is swap the row 2 and row 3. Wait, is that what I want to do? Nah, in fact, no. Let's see. So what I'm going to do now is take, where'd it go? Okay. Row 2 and replace it with row 2 minus 1/2 row 3. Okay, so 1/2 row 3 is, okay, so first copying this one down. 1/2 row 3 would give me 0, 1, 0, 0, 0, 3. Subtracting would give me 0, 0, 1, 1, 1, 4. Right?
0, 1.
Okay, so put that in for row 1, 1, 1, 4, 0, 2, 0, 0, 0, 6. Okay. And then what we have is our leading entry here is more to the left than our entry before it. So we want to swap those two rows, right? So we'll go ahead and swap those now. So row 2 and row 3. We'll just flip the order. And then 6, 0, 0, 1, 1, 1, 4. Okay, how are we doing on time? We're out of time. Okay, we are nearly in reduced row echelon form, right? So we have this echelon or step-like shape, and the only thing that we don't have is that this leading entry is 1. And all we need to do to get that is just multiply that row by 1/2, right? So we just replace this with 1/2 row 2, and then it is in reduced row echelon form. Okay. My column's got a little crooked. So I think I'll leave it there. We can figure out what the solution is, but I'll talk about that next time. So we've gotten to this point. This is in reduced row echelon form, right? So I think the most important thing to practice is just these row operations and just get used to doing those. Should the 6 be a 6? No, it should be a 3. Okay, thank you. Yes. Great. Okay, so that's all for today. And then I'll have some quick exercises to do at the beginning of class, I guess. We'll start with maybe review and then some practice, and then we'll move on. So we are like we're just a little bit into 1.2. So you should, I think it would be helpful if you read over that section before next time, because that will help you kind of get used to these ideas as well. So does everybody have access to the textbook? Yeah, okay.
Not yet.
Not
The
yet?
link to it's on Canvas, right?
Yes. So the info about homework has information about, well, basically you can access the ebook through the homework system. And so
There's a 2-week free trial too.
yeah, you can sign up for a free trial. Homework or practice should we do by Thursday's class? So I can actually put up some like suggested problems from this section if you'd like to. Yeah, I'll post those on Canvas. These will be suggested problems from section 1.1. So that would be the things we talked about before the row echelon form. Okay. All right. So I'll stick around if you have any questions. Just so you know, my office hours are going to be like right after this class. So it'd be 2 to 3. And so you can stick around if you have questions or anything.